Okay, so we're having a look at solving the time of flight for a 47, an isotope of titanium with a mass of 47 in a mass spectrometer. Okay, so we've been given our equation linking our time of flight, T, to our distance in the flight tube, to the mass of our ion, M, crucially not the atomic mass, but we're going to come back to that later, divided by 2 times our kinetic energy of these ions. Okay, so in the equation we've been given the kinetic energy. Importantly, really important concept in mass spectrometry, we aim to ionize all our sample to 1+ ions. This is because this ensures that each ion has the same kinetic energy. This is really the key part of mass spectrometry. This is what means the heavier ions, if you think of the equation for kinetic energy, half mv squared. Well, if the kinetic energy is the same, if something has a bigger mass, its speed must be lower. If something has a smaller mass, its speed must be bigger. This is what's going to change the time of flight and allow us to infer the mass from this time of flight. Okay, so a really key concept in mass spectrometry. Now, the issue here is we are looking to find the time of flight for the 47 ion, but we do not know the distance of this flight tube. Okay, but this doesn't mean we can't solve this equation. And the key here is we're going to have to use the time of flight for the 49 ion. Okay, so the key thing to note here is the distance down the flight tube. I've just said the kinetic energy is the same for both ions. Well, the distance of the flight tube, or the length, of the flight tube, this is also the same for both ions. Okay, so if the length of the flight tube is the same, the first real key part to solving this equation is I'm going to rearrange my equation at the top for this distance. Okay, so the distance down the flight tube, well, this is just going to equal the time of flight times 2 times the kinetic energy divided by the mass of the ion. So all I've done here is just times up by square root of 2e, divide by the square root of m, and we've ended up with this star equation. Okay, so the crucial part here is we're able to solve for this distance using the time of flight of the 49 ion. Okay, so the time of flight of the 49 ion, we know. The kinetic energy that we know, and the mass we're going to calculate shortly, okay, the mass of each ion. So you're completely fine to put this into your calculator, work out a value for this distance, and then go back to our equation 1 at the top here to solve our time of flight. I'm going to do it slightly differently. So I'm going to introduce this notation. So I'm going to say that the distance is equal to T49 means the time of flight for the 49 ion. Okay? And it's going to be times by the kinetic energy divided by the mass of the 49 ion. Okay. Well, this distance, this flight tube length is the same for any ion in this mass spectrometer. Every ion is going to travel the same length. So therefore, this length must also equal the time of flight for the 47 ion times by the kinetic energy of the 47 ion divided by the mass of the 47 ion. Okay. So we can equate these two expressions here. They both equal the distance of the flight tube, so they must be the same. Okay. So what I'm essentially going to do is rearrange here for the time of flight for the 47 ion, okay, which is what we're interested in solving. So the time of flight of the 47 ion, well, that's going to equal the time of flight of the 49 ion. And this is going to times 2 times the kinetic energy times the mass of the 47 ion divided by 2 times the kinetic energy times the mass of the 49 ion. Again, I've just timesed up by the square root of the mass of the 47 ion divided by the square root of 2e. Okay, see here we've got 2e on the top, 2e on the bottom. Straight away we can cancel these out. So it simplifies to this expression here. So the time of flight times by the ratio of the mass of the 47 ion and the mass of the 49 ion. Again, this is pretty intuitive. We should get, this is going to be slightly less than 1, this ratio, because the mass of the 47 ion is obviously less than the mass of the 49 ion. So if this is less than 1, we're going to get a slightly lower time of flight, which is what we'd expect for a lighter ion. Okay, so this makes sense. The last part here is I need to calculate the mass of my individual ions here, okay? So we're not looking at the relative atomic mass, we're looking at the mass of an individual titanium 47 and 49 ion, okay? Well, the relative atomic mass, this gives us the mass of 1 mole of our ions, okay? So the way we're going to calculate the actual mass of each ion is to divide the relative atomic mass by L, or by Avogadro's constant. Okay. We should really convert this into kilograms as well. It's worth noting. You'll see this will end up not mattering, but it's good to do this just for clarity. As we see, we have the mass of the ion in kilograms. This relative atomic mass gives the mass of the ion in grams. So this will be the mass of the 47 ion. The mass of the 49 ion, again, would be 49 times 10 to the minus 3, or that's the same as dividing by 1,000. And again, divided by Avogadro's constant. Okay, so we're going to substitute these into our expression. So we've got the time of flight for the 47 ion. This equals the time of flight for the 49 ion. And this can be times by the mass of the 47 ion, which is 47 times 10 to the minus 3 over L. And the mass of the 49 ion, 49 times 10 to the minus 3, again divided by L. Okay, so we see here we've got a divide by L on the top and divide by L on the bottom, so we can just cancel these out. We've also got a times by 10 to the minus 3 on the top and a times by 10 to the minus 3 on the bottom, so we can cancel these out also. So we're left with this as our expression. And again, this makes sort of intuitive sense. The time of flight for the 47 ion will be less than the time of flight for the 49 ion, and it'll be a less by a ratio of the square root of their masses. Okay? So from here, it's just a matter of substituting in our time of flight for the 49 ion, which was 9.816 times 10 to the minus 7. And this is going to be times by square root of 47 over 49. And this should give us, I'll just put it in my calculator. This should give us, this should say the 47 ion here. This should give us a time of flight of 9.614 times 10 to the minus 7 seconds. Okay, like I say, it's equally valid to just use this equation here to find the distance and then substitute the distance back into this first equation here to calculate the time of flight for the 47 ion. I've just done it a slightly different way, but both methods are equally valid.